Hello friends, this is very important theorem, characterization of basis. I will tell you why this is important. So this is like a very really important theorem, because we will spend time on this characterizations and we will understand thoroughly, so that we will get a good comfortability to work with basis. Okay, I will write the 4 characterization theorem. Let V be a finite dimensional vector space. Infinite dimensional also most of the thing true, but I am dealing with finite dimensional vector space for my purpose. Finite dimensional vector space over F. Then the following are equivalent. We mathematician uses the symbol TFAE. The following are equivalent. Okay, you try to get habituated this symbol. Many times people uses this in lectures. V contained in V is a basis. 2. V is, okay, I will write like this. Okay, sorry, the following are equal. I will take V itself here. V is a set. Okay, V is a basis. V is a basis. V is a minimal spanning set. Sometimes this works and this helps us in proving maximal. V is maximal linearly independent set. Okay, I will explain each and every statement. Every vector from V can be written uniquely as linear combination of vectors from V. Okay, so we will spend some time to understand these statements. Okay, so let's see. V is basis, we know what is linearly independent and spanning. This we know by definition. From here you can see this 1 and 4 are equivalent, just like that, because basis we know that linearly independentness says about a unique combination. If you written something that is unique, that we proved in previous lectures, many lectures we quoted, and every here I want to say every V belongs to V. This word every says spanning. So from from here to here it's coming. So linearly independentness says the unique linear combination, and spanning says that every vector can be written linear combination. So 1 implies 4 is easy. Similarly 4 implies 1 is also easy. The word every says that everything says that spanning. The word everything says that spanning. So spanning is complete. The unique, so that means 0 can be also written as uniquely, right? So I can choose alpha is 0. So uniqueness says that it's linearly independent, no other way to write it. So that says that 1 and 4 are equivalent. So since these are very easy consequences, still I mentioned it because this each and every statement has some purposes that we will later on see. Especially the fourth statement. The fourth statement is very important because defining function. Once you return every vector space linearly and uniquely, it's enough to say the linear maps in the basis. That's why I'm mentioning this. So in other words, the linear maps are completely determined how the image behaves under the basis. Under one basis is enough, because every other element can be written linear combinations of that basis element with uniquely. So for a linear, I mean, from the function point of view, the fourth statement is very important. So you try to memorize at least the fourth statement, or try to understand deeply. Okay, and what is minimal spanning? Minimal spanning means there is no other proper subset spans V. That means if I leave at least one element of V to span, Suppose let's say b like this, v1 dot dot vn. Suppose if I leave at least one element, then that spanning won't be the complete V. It is proper subset of V. This is how the minimal spanning set. No other proper subset, no other minimal subset of V, proper subset which spans. Okay. Maximal linearly independent set. What is maximal linearly independent? It is also same. If you add any more vector, then it is cannot be linearly independent. It is linearly dependent. So I wanted to prove this, and we will spend a good time on this is to get habituated or used to it, so that we will get a good sense of a basis proof. As I already proved, 1 implies 4, so I don't want to prove like 1 to 2 to 3 to 3 to 4, not like that. Okay, so what I will do like this. Okay, 1 implies 2 implies 3, that implies 1. This is what I will prove cycle. Okay, so basis 1 implies we have V is linearly independent and spanning. Claim minimal spanning set. So spanning set is clear because of the assumption spanning set together. I wanted to prove that's minimal spanning set. How to prove this is like minimal spanning set? So I'm saying that no other thing spans. Okay, no other thing spans. It's clear because of the statement. You remember the statement, S contained in V either is linearly independent, it is linearly independent, or there exists a vector which is previous combination of previous vectors, right? So I'm saying I cannot leave a vector. Let's see how I cannot leave a vector. Let v be equal to v1 dot 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 vn, and I am going to leave a vector. Let's say vn. We can order in any way, right? So let's say vn. So if I leave the vn, suppose still I can span. That means vn can be written as previous linear combinations of I1 equal to n minus 1, and which says that this set is linearly dependent. This is what I proved in that section on the previous videos. The set is either linearly independent or there exists a one vector and which is combination of this thing. So we cannot leave any vector, right? If we can leave a vector still spans, means that vectors can be spanned by previous ones, and we can show that, say without law of generality, that vector is n, the last one. So from here it's clear that we cannot leave because linearly independence will go. See that the simple theorem, the simple proposition or theorem, which is very important, right? So we cannot leave. So 1 implies 2. Now let's say 2 implies 3. Minimal spanning set. I wanted to prove maximal linearly independent. Okay, we will prove that. So from here, by the assumption, minimal spanning means no other proper subset is spanning. Okay, in similarly this theorem is very important. We have a set. Okay, let's say this is minimal spanning set, either linearly independent or there will be some vector which is linear combinations of previous vectors, right? So let's say b equal to v1 dot 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 vn. Suppose let's see I have a vi here, and this vi, if it is not linearly independent, I wanted to prove, right, it's a maximal linearly independent. Let me prove linearly independent, then I will prove maximum. I want to claim first is linearly independent. So suppose this vi can be written as linear combinations of alpha I, alpha j, vj, I j equal to 1 to I minus 1 previous vectors. Then the total v spans the capital V along with vi. If I leave the vi, I span v1 dot 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 vn, and I leave vi, and this spans, but still vi will be there, right? Vi will be there because vi is a linear combination of other vectors. So Vi will be there. So still this the space going to be V, the capital V. So leaving Vi is not a problem, because if I leave Vi also, still I can catch Vi using these guys. Okay, so that is not a problem. For the rigorous proof and rigorous thoughts, you have to see Professor Shivakumar video, or you have to read books. Okay, as I said, I am not trying to replace anything. These videos are mainly for the people who already done a simple course in linear algebra. This is kind of a review course. Okay, the people who knows that if you this something is very easy to see. Set spanning is same as spanning over the span. You span and you get a vector space, that is also set, and again span you will get the same vector space. Okay, so from here you can understand that this is very simple to see. So from here I proved that this is linearly independent. Okay, so now we have a linearly independent set and B equal to minimal spanning set, that is assumption set, that is assumption. Now from here we will prove linearly independent and spanning. So that means B is a basis. So we indirectly proved that 2 implies 1, but that is not our aim. Basis. So now B is a basis. Okay, I want to show that this is maximal linearly independent set. I showed no, since B is a basis, so that is a spanning set. Any linearly independent set cannot, there is no other, any linear independent set must be less than or equal to spanning set, right? That I proved in previous lectures. So there is a relation between the linearly independent set and the spanning sets. Spanning sets cardinality always at least equal to or much bigger than this. So I proved that this is like the basis can be the maximum linearly independent set way. So that implies this B is maximal. Because it is not maximal, it means that it spans, there is another vector which I can add and I can make it big, but that is a contradiction to the spanning basis. So this is won't happen. So maximality comes, maximality comes here, maximal linearly independent set. So the now 3 implies 1. So we have a maximal, let's say maximal linearly independent set. I want to prove basis. So basis I want to prove linearly independent and spanning. Linearly independentness here, so I don't want to prove linearly independent, I want to prove spanning. So we will show that it spans. Okay, suppose B, the span of B, proper subset of B, then let V belongs to, small v belongs to the V. This is I can do because I assume this is proper subset. So add this guy. Okay, now this is much big, at least one step bigger than V. The cardinality of V is strictly less than the cardinality of B union 1, because I added 1. We are in finite dimensional finite spaces. Okay, B is finite itself, so it's one step more. This is, let's say n, this is n plus 1, like that. Okay, so I know that, let's say this is S equal to B union V. A theorem that I proved again I'm quoting, that this S is linearly independent, or there exists a one vector which is previously linear combination of previous vectors, that linear combinations of Vi is linear combination of previous vectors. Okay, since V equal to V1 dot 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 Vn, now I am adding another V, so that becomes yes, but any Vi cannot return as a linear combination because this set itself is linearly independent. Okay, this is linearly independent, so I cannot return. So if I return, I can return this V only, previous linear combination. I cannot return here, so this one only I can return previous linear combination. But remember that this V have taken out V minus the span of B, the span of B, right? So from here it says that S must be linearly independent, but that is contradiction to the maximality. This symbol we use as for contradiction, this symbol here we use as for contradiction, and this contains a maximality. because we have one more added, and that says that this is linearly independent, right? So this contradicts the maximality. Hence this is contradiction to the fact that V properly spans, but this V cannot properly spans. V spans full. So I proved the linearly independent by assumption, and the spanning is there, so we are done. So this says that this basis. Okay, so 1 implies 2 implies 3, 3 implies 1, and 1 implies 4 if and only if. That is also proved. But remember that this page is very important. Each and every step has a very significant applications in many places, especially when you are dealing with field theory. This kind of statement will be often used. But as far as function concerned, this fourth statement is very important. Every vector can be written as uniquely linear combination. That particularly says that if you wanted to define a function, a linear transformation between two vector spaces, define in basis. Let's take a basis, define in a basis. In next video I will explain very clear about linear transformation, how to define in basis, and action on the basis determines everything. Once if you understand this action of basis determine everything, then matrix comes into play. Once matrix comes into play, things are pretty clear. Okay, I will spend